quick application to exponential functions to a financial model. So suppose I deposit $1,000 into the bank, and I'm going to get 6% compounded monthly. So what does that mean? It means that the 6% is not a monthly interest rate, but it's a yearly interest rate. And I know there's 12 months in a year, so I'm going to take that 6%, convert it into a rate, which is 0.06, and divide it by 12. So my monthly interest rate is going to be 0.005. Now what does the word compound mean? It means I get interest on interest. So I created a little table here. And my initial deposit, I will call that month 0, and I deposited $1,000. At the start of month 1, I will have gained 0.005 interest. In other words, $5. So my total amount at the beginning of month 1 is $1,005. So in order to compute what I'm going to have after month 2, or at the start of month 2, I should say, I start with my $1,005 and I add to that 0.005 of that $1,005. And I wind up getting $1,010 and, well, 2.5 cents. We'll leave the 2.5 cents in there numerically. But what happens at the beginning of month 3? Well, I have to take this amount and calculate the same thing using that. And I wind up getting $1,015 and a little over 7.5 cents. So why is this an exponential model? Well, if I look at this division and I look at this division, I wind up getting a constant ratio of 1.005. But that was just this, 0.005, and it's adding 1 to it. So the base for these things is going to be 1 plus the monthly rate, which is that, or whatever compounding rate we're dealing with. So our base is going to be 1.005. But our initial value, that was given in the problem, that was 1,000. So the amount of money that I have in the bank after T years, and I usually use T for time, is given by this model. Now if you're going to use Desmos, type in f of x equals 1,000 times 1.005x. Let's move over to Desmos. So in Desmos, what I'm going to do is I'm going to type in f of x equals, now my initial value times this 1.005, and I'm going to raise that to the x power. And it's automatically going to put a graph in for me. Now, you might need to zoom in or zoom out. I am using the mouse wheel to do that. You can drag it around if you need to see things. So why is this really helpful? So one thing I could do is I can take what happens after 12 months. And it's $1,061 and, well, about 68 cents. I can also figure out what happens in 10 years. Well, I get $1,819 and looks like 40 cents. Another nice thing about this is if I want to actually plot some things, let's say 100 months out, I can type in 100, f of 100. And there's a little label button here. If I click on that, it actually labels my point. So this means after 100 months, I will have $1,646.67 in the bank. That's if I don't touch it. That's 6% compounded monthly. I hope this was helpful. So this problem has 4 parts. So suppose you deposit $1,000 into the bank at 8% interest. I want you to compute 4 numbers at the end of this. After 30 years, how much would you have in the bank if this 8% was compounded monthly? Part B, quarterly, that's 4 times a year. Daily, in other words, every day they're going to put money into your account. Just assume that there's 365 days in a year. Don't count the sleep year stuff, I'm not going to bother with that. And then every minute. Still assume that there's 365 days in a year. So I hope you were able to solve some of these on your own. So in this particular problem, we have an 8% interest rate. So I know that compounded monthly is going to look like 0.08 divided by 12. And then the quarterly is going to be 0.08 divided by 4. The daily, 0.08 divided by 365. Now what about the every minute? Well, I need to figure out how many minutes are in a year. I know there's 365 days in a year. There's 24 hours in a day, give or take. There are 60 minutes in an hour. So that's how many minutes are in a year. So that's my denominator of the 0.08. So if you notice, each one of these rates is going to be 0.08 divided by something. Now 30 years. I need to look at 12 times 30. That's the number of months, the number of compound periods that we're going to have. Over here, it's going to be 4 times 30. That's the number of quarters in 30 years. And this one, it's going to be 365 times 30. And this last one is going to be 365 times 24 times 60 times the number of years. So this is how many minutes are in 30 years. Let's jump over to Desmos to do a few little calculations. So in Desmos, what I'm going to do is just use this as a straight calculator and not really as a graphing device. So I can type in 1,000, that's my initial rate, and I know since I'm dealing with compound monthly, it's going to be 1 plus 0.08 divided by 12. And that's my monthly compounding rate, but then I need to raise it by the number of compounds I'm going to do, which we already wrote out as 12 times 30. So after 30 years, we're going to have $10,900 and about $36. That's the monthly rate. Now, what do I need to change on this? I copy and pasted to wind up getting the quarterly rate. Well, the only thing I really need to do is change this 12 to a 4. I'm going to change that to a 4. And then I evaluate it. So I want you to notice that my monthly compounding and my quarterly compounding, the numbers are different. The more I compound, the more money I'm going to have. So that leads me to, well, I think I know the answer to this, but if I divide this by 365, and then 365 days, I even get more than the monthly. This is the daily rate. Now what about that every minute? Well, this denominator is now going to look like 365 times 24 hours times 60 minutes in an hour. So that's my denominator. And my exponent is going to be my 365 times 24 times 60. although compounding every day and compounding every minute differs by, just under $3 it looks like. Compounding every minute is even better. Well, can I do even better than every minute? Can I do every second? I know this wasn't part of the assignment, but what I need to do is multiply this denominator by 60 and change this exponent by multiplying by another 60. Every minute and every second. Which one's bigger? Well, it looks like every second is just ever so slightly bigger. Now, can I do even better than every second? Well, whoops, got rid of it. I'm trying to copy this. The expression is getting quite large. What happens if I multiply this, say, every millisecond? So I tack on 1,000 in there, and I multiply this by 1,000. So this is every millisecond. Do I get much more money? I just get a little bit more. So this idea of compounding more and more is called continuous compounding. And we'll talk about that in a later video. So to come back to things, my answers for this particular problem, and I'm just reading off the screen that we had before. This was $10,935 and about 73 cents. The quarterly was $10,765 and about 16 cents. The daily looks like $11,020 and I think 28 cents. Every minute was $11,023 and it looks like 17 cents. Now this idea of continuous, or every second, was not much more than this. $23, and it was still, actually, it rounds up to 18 cents. And every millisecond, whoops, I messed up second there. I get $11,023 and it looks like 97 cents. So the more you compound, the more money you make. But there is a limit to this. No pun intended there, sorry. I hope this was helpful.